next speaker is Heather Cegla, and she's going to tell us about how to use transits to tell you something about the magnetic field structure.
Yeah. And I should be here. Okay. Yes, I'm turned on by the microphone, so that's good. So hopefully you can all hear me in the back. I'm Heather Cegla. I am a KOPS fellow hosted at the University of Geneva, and I'm going to bring us back to the sun for a start. We'll go to different spectral types. So I am interested in stellar surface convection, and so that's what I've got playing here. So I look at it from a simulation point of view. We have our own 3D MHD simulations here on this side, about 12 megameters by 12 megameters in the horizontal direction, and about 2 megameters in the vertical direction. So these are box-like simulations. And courtesy of Chris Watson, we have an accurate map of Europe to scale here for you. And then we have solar observations here of about 30 by 30 megameters here to put this in perspective a little bit more for you. So as others this morning talked to you about, we have these hot bubbles of gas, the granules, that are rising to the surface. And if you are observing the star, then those are coming towards you, so they're blue shifted. And then as they cool off, they fall back down into the intergranular lanes, and they are red shifted relative to your line of sight. And so these upflows and downflows create asymmetries because they don't completely balance out. So if you're observing your star and looking at your stellar lines, you have asymmetric profiles and a net convective blue shift because your granules are larger and they cover more surface area. And of course, we don't just look at the dissenter of stars, we also observe them as a whole. So we're interested in the center to limb phenomena. And so that's what I'm showing you here. On the top right-hand side, you can see the line of sight velocity. And so it's a little bit different color coding from the previous talks. So because it's line of sight velocity. So here, blues are blue shifts, so the granules are blue, and reds are red shifts. And then in the bottom here, I'm showing you the continuum intensity. And so you can see the corrugated structure changes what we can actually view. So as you go towards the limb, all of a sudden the granules are obstructing other granules. You can't see the very tops of them. You can't see into the very bottoms of the lanes. You have velocity flows that were horizontal at this center that as you go towards the limb now have a line of sight component. And so you can see all of those different line of sight velocities and continuum intensity variations impact your line profiles and your net convective blue shift. And that's what I'm showing you here in this plot. It's where we've taken the line profile from our simulation and we cross-correlated them with a template at this center. So this shows you, in our simulation, what the net convective blue shift is as a function of center to limb relative to the stellar disk. And so this sort of phenomena is happening all over your star, and it depends on your spectral type and everything. And so, of course, our simulations are only important if they're actually realistic. And although the MHD simulations have been highly tested at dissenter, it's still important to extend that to the limb. And so that's what I'm showing you here. This curve may look different than the other one, but that's because now we're looking at an absolute scale, and instead of a cross correlation, we're measuring the line center. And so the difference between red and green I'll get to later, but the important thing is this is my simulation here, and these are actual empirical observations from the large spectrograph on an absolute scale here. And these have a magnetic field of the quiet sun, and what we're looking at is closer to 200 Gauss. It's a little bit more like a facular or plage region. And we'll get to why that's important later, but why the thing that may be striking you here is these curves look relatively different. You might not believe me from the first go that, oh, this is a validation of our simulations. And actually, we believe the differences here are because of the magnetic field. We know the magnetic field inhibits the convective flows, so we expect there to be a red shift relative to the quiet sun. And there's different line of sight contributions means actually this sort of turnover here changes as well. And to convince you a little bit more, We also looked at simulations where it's the same underlying code, which is the MIRAM code, and we said, okay, now instead of a 200 Gauss field, let's say the net field is 0 Gauss. Now we match very well the shape. We're off a little bit here, but that could be because our seed field for the magnetic field is a little bit different from the quiet sun, etc. So if you want to know more about this, we have more comparisons with observations in our paper, which is on arXiv today. So download it, check it out. You can even see the comparisons with the HMI observations, where Raphael Hayward will talk a little bit about how you can use observations of the sun and split them up into different regions of magnetic activity. And we see actually on the sun, if we look at differently magnetized regions, we get this same sort of behavior as well. And so for my stuff, I'm interested in going one step further. I want to parameterize the granulation signal so that I can create line profiles that are representative of what we would get in the computationally intensive radiative 3D MHD simulations, because those things take a long time to run, and I want to create artificially noisy stars that would have convection all over the surface and realistic convection on the centimeter per second level. And so what we do is we take cuts in our simulation between continuum intensity and magnetic field. And then that means for every single pixel in here, we have all 4 Stokes profiles. I'm interested in the Stokes eye or the absorption lines, because as someone who works in spectroscopy, that's primarily what we observe is the absorption lines. And we say, okay, now we have these different 4 components here, color-coded. We know the granules are bright and non-magnetic, so that's one. Oh. And we know that in the intergranular lane, we have magnetic regions and non-magnetic regions. And we also, if you have concentrations enough of the magnetic field, they can be bright because you evacuate your flux tube. And so this is showing you the corresponding line profiles for the different physical components of the granulation. And you can see how they change as a function of center to limb here. And so, again, the granules here are the green ones, and then you got your magnetic components with the Zeeman splitting happening here, and then the purple one is your non-magnetic intergranular lane. And these are changing relative to each other, their Doppler shifts, because of those line of sight flows, and their intensities are changing. There's some limb darkening in there and just corrugated effects. And so to diagnose more details about actually the behavior of those individual components, again, go ahead and download the paper and check it out, because there's a lot more details in there. And so the idea is we can take those 4 components, and then we have probability distributions from a time series of our simulations. And we use those probability distributions and the 4 average components together to create new line profiles that would be realistic and what we could get out of the simulation had we run it for a longer time. And we tile those all over a stellar disk, and then we integrate it up to simulate an observation. And then you can see the line bisector here is this nice characteristic C shape. It's been blown up here so that you can actually see the curvature. And if you examine that a little bit further, you can see that the line profile is actually bouncing around on the several tens of centimeter per second regime. And so the idea is, if you can study the shape of your absorption line profile, that should give you information about the convection itself. And if you are interested in high precision radial velocities, maybe because you want to find an Earth analog planet of 9 centimeters per second, then you can actually use this information. And so this is what I'm showing you here. This is just a measure of the curvature of the line. It correlates very well with the radial velocity. You can remove this and reduce your noise. And again, we want to probe this for other stars and to validate the simulations for something other than the sun. Because the beauty about the MHD simulations is that you can go to other spectral types. So we take out-of-transit observations, subtract in-transit observations, and you isolate the starlight behind the planet along the transit cord. And these are the local profiles. I operate on the cross-correlation function because that's basically just boosted the signal to noise coming from your individual line profiles. And to do this for ground-based data, you need to normalize by the light curve, but then that allows you to do a pure subtraction here, and you don't have to assume anything about the local profile shapes. And you may notice that there is Doppler shifts from here to here, and that is because the star is rotating. And classically, you would hear this as the Rosetta-McLaughlin effect, the fact that you go over different amounts of stellar rotation. And so you can actually see that's what I'm showing you here. It's the local RV underneath the planet along the transit cord. And this is for a really nice system called HD 189733. It is a K-dwarf. And because we allow for differential rotation in our simulation, or in our model, because this is actual observations here, you can actually pull out the stellar latitudes and break the degeneracy between the amount of differential rotation going on at the center towards the limb. We can put constraints on the differential rotation, which is really important for constraining your dynamo theories and things like that. And if you're interested in the dynamical history of the system, you can get the projected obliquity between the orbital plane and the stellar spin axis. And you may notice this is quite small, and that's why you only get different latitudes near the limbs. I have an espresso proposal that's just been accepted where we will be looking at systems that should target more stellar latitudes. And in this way, because we get the differential rotation and the stellar inclination, we can break the degeneracy again and get the 3D obliquity of the system, which is really powerful. We've done this for a G-dwarf as well, and we did this for the first time for an M-dwarf. So go ahead and check those out. And for the system that we had the best signal to noise, which was HD 189, we can go further, and we can use this to validate our MHD simulations. So this is the first time that this has been done for something that is main sequence and isn't the sun, because usually it's either the sun or giant stars. And you can see we've got different colored lines for different iron lines that we simulated, and we have different line styles for different magnetic fields that we simulated. And there are trends in both. And we see you have a larger center to limb variation in your net convective blue shift if your lines are deeper, and also if your magnetic field is lower. And that kind of makes sense because your magnetic field inhibits your convective flows. And so we find very good agreement between these two. And again, with my espresso proposal and going on in the future, we're hoping that going to a telescope with a bigger collecting area and a spectrograph with higher precision, we can pinpoint these a bit further. And so I will just leave you here with my conclusions, and if you have questions, I'd like to take them now. Thanks.
Questions for Heather?
I'm Symmetric Space Science Institute. Very nice talk, and I'll ask you about oscillations because I didn't see them in your bisector as you showed with time. What was happening there?
So the reason why you don't see it in the bisector there is because we only have granulation in that simulation that I showed, and that's because those individual 4 components are created from a time average. And so in that way, we just have the granulation. But we do actually naturally have the oscillations in the original simulation. From the MHD, those are naturally excited. And the reason in particular why I wanted you to ask me about oscillations is because from a high precision radial velocity point of view, those oscillations, as you would expect, are going to move your line profile on big scales. And if you're interested in trying to push to 10 centimeters per second and actually get everything out of your spectrograph, then you might want to get rid of the oscillations. And I have a paper coming out, hopefully we'll submit it next week, where we have showed that if you fine-tune your exposure time to your stellar host parameters, you can average out the impact from the oscillations to 10 centimeters per second. For the sun, this is 5.4 minutes. If you actually go a little bit further, like around 8 minutes, you're doing worse because you've sort of allowed part of another oscillation timescale to influence you. So you're not just 1 lifetime, you're 1.5 lifetimes. And if you double your exposure time, you really don't do that much better. And it's not until you really go further that you start to get a monotonic decrease. So in this paper, we will allow you to input your own stellar parameters and say, okay, how do I fine-tune my observations? And you'll be able to just plug that in a relation and get it out.
Jeff.
Hi, it's Ricky Eglin from the High Altitude Observatory. I wanted to ask about the differential rotation estimate from the planet transit technique. Do you have an estimate of how strong of a differential rotation you might be able to detect in terms of relative shear? And is it a true differential rotation or is it a lower limit?
So for the stuff that we have here, it's just constrained because we say that alpha, which is d omega over omega equatorial. For the sun, it's about 0.2. We just put quite a big range on it, but we can say with 99% confidence that it's greater than 0.1. And if we occult more stellar latitudes, we can really constrain that better. And also if the differential rotation is a bit bigger. But I think just going to systems where you are more likely to transit different latitudes, or if you have more transits, so you have more data, you should be able to put more constraints. So at the moment, it's more or less a lower limit, but in the very near future, we hope to really pin this down and that it should be applicable to a large variety of systems.
Jeff.
Okay. You've computed asymmetric line profiles as a function of position on a star in all 4 Stokes vectors.
No, only Stokes I.
Only I?
Yes.
Okay, I thought you mentioned Stokes
We do have
Z.
all 4 Stokes, but we only did the parameterization on Stokes I. We do actually have all 4 Stokes profiles from the center to limb, but we haven't fully analyzed the other ones.
Okay. Here's my question for the future. Namely, people who do Zeeman Doppler imaging, right, use V and the other Stokes vectors, assuming symmetric line profiles.
Yeah.
So my question is, do you anticipate that using these asymmetric line profiles will significantly change the results of Zeeman Doppler imaging?
It's definitely possible. I would absolutely expect there to be changes. As to what level those changes are, I think that's still a little bit in the air. So along those same lines, we've looked at how the asymmetric line profile can impact your Rossiter-McLaughlin analysis and what you derive to be your projected obliquity. And we showed that if you assume you have a Gaussian profile everywhere, so it's symmetric, and actually you have something that should be asymmetric and is changing, you can have systematic errors in your obliquity of 10 to 20 degrees. So in that case, it is significant and it's changing it, but it's not changing it so that it's completely misaligned. So I would anticipate it's probably similar for the ZDI stuff, as you'll probably get significant differences, but perhaps won't fundamentally change the conclusions.
Okay, thanks, Heather.